Let's dig into how we build the networks themselves. We have some design choices to make. We've talked to our internal users and figured out exactly what type of AI workloads that they will be deploying, training, inference, multi-tenant. We're going through the discovery process and understanding what the traffic patterns might be like. So now we want to get down to actually dimensioning our network and understanding how we're going to construct that from a physical and logical standpoint. So the first and easiest choice, classic design, is a fat tree. So we've got over here, we've got a rack with 2 nodes in it. Those nodes have 8 GPUs apiece. We have a top of rack switch connected to all of our GPUs. And a fat tree simply, as you may know, says we're going to have for every link down here southbound of the Tor, we're going to have the same number of links northbound from the Tor into our spine layer. Now, this is guaranteed to give us the amount of bandwidth we need throughout the entirety of the network. The problem, of course, is now we're very much dependent upon the radix of our spine into how big we can dimension our network. One of the most important things about an AI network is bisectional bandwidth, which means what is my guaranteed bandwidth from end to end at any 2 points of the network. And so with a fat tree, not only do we not have the best bisectional bandwidth, we have the best bisectional, we don't have the best radix, right? We can't build it as big as we might need to if we have a large number of GPUs. It's also the most expensive option because for every single link, we're duplicating that link northbound through the network. And so ultimately, the size of our network will be limited when we use fat tree, and the expense will be much higher. So what we've done in classically in networks, of course, is to go to a spine leaf design or a CLO design, folded CLO. And so essentially what that means is from every Tor, you have some construction like this. And in this way, we can have some level of oversubscription at this layer, whatever you're comfortable with as a network architect, whatever the requirements of the use case might define or be acceptable. And in this way, we also have resiliency through the network, right? Because we're connected to all of the spines, all of the Tors are connected to all the spines. We actually have some advantages here in terms of multipathing and resiliency throughout the network. So these are a classic data center design here, spine leaf, that gives us high performance with an AI network. We just need to be aware of what our oversubscription model here might be, because that will ultimately define how big the entire cluster can be, the number of GPUs that we can serve. We have the fat tree model, which gives us the highest level of performance, ends up constraining the size of our network, but gives us the highest bisectional bandwidth from end to end. Okay, those are some classic designs that we can use to build highly performant AI network clusters. But there are other technologies that we need to consider which might influence our design and construction, both logical and physical, of the network. So let's talk about really what the state of the art is. If I'm deploying a large AI infrastructure today, I'm more likely to see this design that I'm about to describe to you, and that's called the rail design. So remember, we talked about the scale-up technologies which exist inside of each of the GPUs. That's NVLink, Infinity Fabric, which allow GPUs within a node to communicate with each other at high speed. Here I've shown you 3 nodes with 8 GPUs apiece. And so that is to say, if GPU A needs to communicate for some reason with GPU H in this node, whether it's training or inference, it does make a difference at this point. If it needs to communicate between here, it's going to choose to use that scale-up network inside of the node because they're adjacent to one another. Its first forwarding decision is to look and see if the device I want to talk to is connected to that very high-scale internal network to the node. So we have this ability to have communications paths within these 8 GPUs right here. And so too, this node can communicate internally, and so too this one. So when we have that additional communications capability, it changes our thought process for how we connect to the rest of the network. So we talked before about a typical spine leaf design, that we would have all of these devices connected to the Tor and then connected to the spine above that. Instead, once we have this ability to communicate inside the node, it changes our thinking here. Now what we want to do is we want to start to connect the GPUs to the same Tor based on their position in the node. So we want to connect all of the A GPUs to A Tor, all of the B GPUs to B Tor, all of the C GPUs to C Tor, and so on. So let's step through why we want to do that and how it creates efficiencies. So if I am GPU A and I want to communicate to any other GPU A, I'm going to have a single hop which gets me to that GPU. No longer, think about it this way, if I was connected to this TOR, every device was connected northbound here, and so too there. If I'm A and I want to speak to one of these other A's, I have to make it to my TOR, and then I have to transit a spine and come back down and communicate with A, because there's no connections between the TORs at this level. I have to go all the way through a spine in order to communicate with another A. In this methodology, if I'm A, I'm one hop away from talking to another A, and so to B and also C. So in this way, we can start to create efficiencies and leave the spine capacity for when we have flows which leave the dimension of the TORs that are connected right here. So this is a highly efficient way. This is called the rail design. It's a highly efficient way to create efficiencies in the network, yes. If you're starting to use, if you think about some operators which have very large infrastructures, they may not choose to have a small TOR. They may choose to have chassis-based devices here so that those chassis connect to many hundreds of GPUs, and they can have single hops between many hundreds of GPUs before it ever reaches a superspine layer. So connecting the devices in this way in the rail design allows us to leverage the scale-up network, which is here inside of the node, and also creates additional capacity in the spine layer for interconnection between the racks themselves or perhaps the pods. So we talked about the logical and physical designs of an AI cluster. Now we're going to talk about congestion control, because when we were in the training section, we talked about the massive amounts of data which are being transferred from place to place on a very regular basis, leading to incast and head-of-line blocking problems. When we talked about inference, we talked about the need to reduce latency. And in order to do that, we want to make sure we have a highest performing network that's using all available capacity. So what are the techniques that we can use in order to have the best possible network? Well, our first line of defense is Multipath, is using all of the available paths and capacity in the network. So we have a couple different choices here that we can stack together. The first of which is ECMP. So ECMP is multipath on the IP layer, the ability to spread traffic around across links, potentially move traffic based on congested links. This is our very first line of defense. We can also operate as an industry. It depends on vendor implementation here. Most of this does. There's going to be some vendor variation here. I'm describing everything for you. But we can also operate on the InfiniBand Q pair that's available inside of the packet itself. So we have an additional source of entropy to spread traffic around and balance links and use the complete capacity from end to end. So Multipath, a very powerful tool, as it always has been, for making sure we're getting the most out of our investment in our network. The second piece is some classic congestion control algorithms which are used in combination, the first of which is ECN, explicit congestion notification. ECN is a mechanism for any two stations in the network to be able to communicate and provide some back pressure to the sending station. So if a receiving station is experiencing congestion, it's going to use some bits in the frame, send it back towards the sending station. Sending station then can back off and ramp its traffic back up. It's a pretty coarse mechanism. It's something that a receiving station sends out and is operated on by any of the transmitting stations, and so we want to use it sparingly, but it is a key source of congestion control in today's artificial intelligence networks. We use that in combination with PFC. So PFC is a hop-by-hop mechanism. So now think about a switch or a router who has a certain set of queues configured. One of those queues is going to be the AI traffic itself. And when that queue gets to a certain depth, we have an awareness of that, and we can propagate through the network information that basically receiver or sender stops sending traffic to us. So based on the queue depth of any individual element in the network, we can provide some back pressure and have the sending rate slow down. So between ECN, which is end-to-end, PFC, which is hop by hop, we have two tools that we can operate together and provide some sort of congestion control in the network that gets us to a very, very high level of performance. So you'll see these two in combination very frequently. They're very well supported by a large number of vendors, and between that and multipath techniques, that is our baseline for today's artificial intelligence congestion control networks. That's kind of the bare minimum you would need in order to support today's applications in AI. So there are some other techniques that are emerging as well. One very interesting one was proposed by Meta a little more than a year ago. They gave a public talk where they started talking about how they use traffic engineering to gain performance out of their Ethernet network. Now remember, Meta just released, as I record this about 2 or 3 weeks ago, just released Llama 3, a 405 billion parameter model, absolutely massive model. And in their white paper that they released describing the training process, they talked about the fact that they used Ethernet exclusively to train the biggest model, the 405 billion parameter model. And they state that they got equivalent performance to InfiniBand. Now, Meta also have a bunch of InfiniBand equipment. They've been vocal about that. But they said for the 405B model, they actually used Ethernet with equivalent performance to InfiniBand. This is massive news, right? Because now we're talking about having all of these other pieces available to us, but they chose to use a traffic engineering technique, which I'll describe right now. What they said is because they know in advance which GPUs will be used for any given job in their network, they might have some constellation of GPUs. They don't use the entire node, they use portions of it because it's a multi-tenant system. They actually have designed a controller that is linked with their job creation engine. So you have your AI software stack that's doing the communications collectives that we talked about before. Those communications collectives are aware of which GPUs will be engaged during the AI run, training or inference. And so they've created a controller, let's think of it again like an SDN controller, that does a constrained shortest path first algorithm on the design of their network. So it understands this network, how it's constructed, it understands the underlay here, and this controller then programs each of the TORs with traffic engineering information to optimize the path, to effectively give a clear path from place to place in the network. So in this way, they are able to, along with some other techniques like giving multiple IP addresses for every GPU to create some more entropy in the network, but they are able to program with some lightweight static routes in each of the TORs for the duration of the job. They're able to create an overlay network which gives them extremely high performance in the absence of some of these technologies up here. So they exclusively use, according to their paper, this traffic engineering technique in order to get the same level of performance from their Ethernet infrastructure that they get from their InfiniBand-based infrastructure. This is massive news, right? This is a very interesting and novel technique that is going to lead to a lot of research on the part of the vendor and research communities to try to replicate this and understand whether something lightweight like this traffic engineering scheme could actually alleviate some of the operational complexities that you might experience when you're using a combination of congestion control protocols. So moving on, one of the other questions that were asked quite a bit is how much buffering do I need in the network? So if you take a look at the leaf spine design, it's often based on some merchant silicon, Broadcom being the primary supplier here, but there are others. And generally, in a classic data center network, we'll see lightly buffered TORs and we'll see deeper buffered spines. And people ask, is that still the right model? I think there's not a lot of alignment on whether buffering is needed in an AI network or not. Some very large operators have been very clear that they have successfully used buffering and take advantage of it. It offers something to them in performance. Others, for example, don't use chassis-based spines. They use small TORs and they just replicate that throughout the network and manage over subscription. And so they're using lightly buffered devices throughout the entirety of the network. I would say that as you're designing your AI network, you should look at the use cases, go through a discovery process with your internal users, operate with your vendor partners, and make a determination what the right combination of buffering is in the network. Buffering obviously interacts with some of these protocols here. Something like priority flow control would be more effective, I would think, if you had deeper buffers, but that's maybe not necessarily the case depending upon the type of training you're doing, the model sizes, the choices you make in terms of the block sizes inside the model. There's so many tunable parameters that you really need to dig in and work very closely with your partners internally and externally to make a determination what the right platform for you is. Finally, I want to mention scheduling. So there's in the vendor community now, there's some discussion of scheduled fabrics from end to end. So this effectively says that I have some platforms, TORs that are operating as line card chassis, right? They have Ethernet that goes down to the GPUs just like normal, but instead of an Ethernet-based spine layer, they have some other spine layer up here, right? And that is, it could be cell-based, it could be frame-based, but nonetheless, it effectively is not a standardized layer of communication. It just operates as a deterministic fabric inside the network. So you might call this disaggregated, right? Where you have different boxes that serve different functions, and this layer is a fabric, a proprietary or at least not an Ethernet fabric, and this is Ethernet connections down on the bottom, which provides your standard space connectivity. So, first of all, if you were to wrap a piece of sheet metal around all this, that's most vendors' chassis-based systems, right? You would just look at this as the backplane, the backplane fabric, and you would look at these as the line cards that you put in. So we know the model well. This expands upon a time-tested model in the networking industry. The advantages of a scheduled fabric, as some would say, is that I don't have any contention in the spine layer here, in the fabric layer, because I'm creating a virtual output queue. If I have traffic coming in here and it's leaving here, I can set up a virtual output queue here that modifies the behavior of my egress traffic over here. I can actually manage traffic here for traffic that's leaving there. Same model as we have today with a chassis. The downside to a scheduled fabric is that, number one, you're generally locked into the same set of vendors for every piece of equipment in your network, because once you make the choice to build a scheduled fabric using disaggregated equipment like this, you're very much locked into a generation, you're locked into a vendor choice that you have here. The second piece is that the question is, does it really gain any efficiencies now that we have not only the standards-based techniques that we've talked about, which are very common, but some of these emerging techniques which allow us to more deterministically pass traffic through the network. So there is a question that, scheduled fabrics, there's several vendors which are providing options here. It does tend to look a little bit more like the InfiniBand model. You get some guarantees at the expense of a reduced ecosystem. And so what I would say is, as part of the discovery process with your use case folks, you'll want to make a determination whether something like a scheduled fabric makes sense, gives you the performance efficiencies versus the trade-offs that you'll make in terms of the smaller ecosystem and potentially the added expense.